Okay, so on to question 2M2 from second edition of Statistical Rethinking. This question is very similar to 2M1, so if you haven't solved that one or haven't watched the video on it, you might want to do that. So the question though is, now assume, okay, let's go up to the first question just in case you haven't seen that one, otherwise that question there won't make any sense. Where are we at here? Okay. Question 2M1, which is being referenced in the next question that we'll solve, recall the globe tossing model from the chapter. Compute and plot the grid-approximate posterior distribution for each of the following sets of observations. In each case, assume a uniform prior for P, where P represents the proportion of the globe that we're tossing around represents water. And so now, so the idea is that we're throwing around this globe. Every time we catch it, the person who catches it has their index finger on either water or land. And so we're trying to use the data, the observations that we collect by tossing this ball around and seeing where somebody's index finger lands to estimate what proportion of the globe is covered in water. And the three cases that we see, or the three sets of observations that we get, are here: water, 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 land, etc. So that's the question that's being referenced in this next question. I guess what's going to differ is that in this problem, 2M1, it asks us to assume a uniform prior for P, the proportion that of the globe covered in water, and that would just look like a flat line across all possible values for W grid, where every value of W grid represents a value for a potential proportion of the globe being covered in water. Okay. So, having said that, let's get back down to 2M2. Now the question asks, now assume a prior, which again is the proportion of a globe covered in water, that is equal to 0 when that proportion is less than 0.5 and is some positive constant when, typo there, when P is greater than 0.5. Again, compute and plot the grid-approximate posterior distribution for the same sets of observations that we saw above. Okay. So hopefully you understand the setup again. Now, again, like the question says, now we're not assuming a uniform prior. We're saying that for proportions of water less than 50%, we're going to say, we're assuming that that's impossible. Okay? But when it's greater than 50%, then we're going to, greater than or equal to 50%, that should be, then we're going to assume a constant level of belief. Okay, so we'll get into that here. This code is just copied from above, but again, W grid is just going to be a value for every proportion of water that we're going to consider. And now we're going to use as a prior no longer a uniform prior, but one that looks like this. Okay. So down here is W grid, which again is the proportion of the globe covered in water, and it's 0 for all values up to 0.5. And then once we go to or above 0.5, then we have one value that's the same for all of them. Okay. Now here we've used a value. Okay, when W grid is not less than 0.5, we've used a value of 1. This is not really important. We could put any value here, and it's not really going to affect our results, but that's fine. So all that's important is that each of these values along here has the same prior probability associated to it. Okay. So having said that, now we have our different likelihoods. So again, we are going to model the likelihoods as binomial distributions because the globe either has, when we catch the globe, our finger either lands on water or on land. And so there's two possible outcomes, and we can model that with a binomial distribution. So this is 3 waters in 3 different tosses, 3 water in 4 tosses, 5 water in 7 tosses. Okay, and so this code right here is going to give us a value for the probability of this observation for every value in W grid. The probability of this distribution, or I'm sorry, of these observations for every value in W grid. Okay. And so again, these are the same, these are identical, code copied exactly from question 2M1 above. Okay, so again, hopefully you've seen that video. But now we're going to combine our new prior, again, which looks like this, with these different likelihoods. The way that we do this again is with we start by multiplying the prior times the likelihoods, okay, each all by itself. And this is going to give us an unnormalized posterior. Again, I explained that in the video for 2M1. In order to normalize it, so in other words, so that our posterior is a valid probability distribution, meaning that that the area under each of the curves that we'll see represents 100%, we need to divide the unnormalized posterior by a normalizing constant that we're calling the marginal probability. And the way that we calculate that is for marginal 1, for the first set of observations, we just take every value that we found here, right? So this is going to give us a value for every, this is going to give us an unnormalized probability for every value in W grid, and so we're just going to add all those together, okay? And then we're going to divide, so our posteriors, our normalized posteriors, are going to be the unnormalized posterior divided by the marginal for that, okay? And then I'm going to plot that, okay? And so we have each of our sets of observations here, so just quickly going through this. So the top row is the priors, and again, the prior is the same for each set of observations. 0% prior probability when the proportion of water we're considering is less than 50%, and then some similar amount or identical amount for when we're considering values greater than 50%, greater than or equal to 50%. Here are our likelihoods. Again, these are exactly as we saw above. And then the posterior is just simply combining the prior and the likelihood. Okay, combining prior and likelihood, combining the prior and the likelihood. And what we see is that the posterior has a shape that's kind of a child of the prior and the likelihood, right? So for each of the posteriors, we see that that the likelihood has been changed, or that's a weird way to say it, but the shape of the likelihood has been changed so that everything is 0 below 50%, and then once we get above 50%, it is identical to what the likelihood is.